Hey everyone! In this video our objective is to address old Regents questions related to the math of formulas and chemical equations. Okay, so here's number one. Given the formula for a compound, we're given this structural formula which represents an actual formula or an actual shape of a compound with the actual number of each element in the compound. So it's not reduced to the simplest whole number ratio. It is what the element truly is. So here's the question. Which molecular formula and empirical formula represent this compound? Now to address this, we need to count how many of each we have to begin with. So we've got carbons, and we have 1, 2, 3, 4 carbons. We've got oxygens, and there are 1, 2, 3, 4 oxygens. There are nitrogens present, 1, 2 of them, and hydrogens, there are 2. So we are looking for a molecular formula that does not alter from these ratios. So that's either this one or this one. Now, in looking at this question, I do realize that it did copy incorrectly, and you'll see here that I hand wrote in some of the choices. And, well, now we have to relate to the empirical formula, and the empirical formula is the simplest whole number ratios. So if we were to, once again, inspect these ratios, if we wanted to make it the simplest whole number ratio, we would divide each number by the smallest number present and hope that it leads to whole numbers. So it does lead to 2 carbons, 2 oxygens, 1 nitrogen, and 1 hydrogen, and that is represented right here. The answer is D. Number 2. Given the two formulas representing the same compound, so they are the same compound, but one is expressed as the simplest whole number ratio, 1 carbon to 3 hydrogens, and the other one is a multiple of that, 2 carbons to 6 hydrogens. Which statement describes these formulas? Formula A and B are both empirical? No. Formula A and B are both molecular? No. Formula A is empirical, simplest whole number ratio. Looks good. Formula B is molecular. It is not expressed as the simplest whole number ratio. Absolutely. The answer is C. Alright, now on to number 3. What is the gram formula mass for ammonium phosphate? Now the gram formula mass is very similar to the mass expressed in AMUs, but because it's out of 1 mole, it actually bumps it up to a usable scale. So instead of AMUs, we're going to say grams per mole when it comes to the mass for each of these elements. So let's inspect what we have here. Nitrogen. How many nitrogen or moles of nitrogen do we have? And according to this 3 here, applied to the ammonium, we've got 3 moles of nitrogen. How many moles of hydrogen? Within the parentheses we have 4, but the 3 multiplies it by 3. 3 times 4, we've got 12 moles of hydrogen. How many phosphoruses do we have? And that is but 1. And how many moles of oxygen? We've got 4. Now what is the mass of each of these? Because we have to multiply how many moles by the mass. And for that we are going to look at the periodic table itself, and nitrogen's mass is located right here. And let me make it larger for you. Moving on over. There it is. Nitrogen's mass is 14.0067. We're going to round that to 14. And while we're here, let's look. Oxygen's is 15.9994. We'll round that to 16. And what other ones are present? Nitrogen, phosphorus is right here. We'll round that to 31. And hydrogen lives on the other side, right here, and it will round that to 1. Now I see that everything I wrote disappeared as I was sliding things around, so let's just recreate that. Nitrogen, we have 3 of them, and 14 grams per mole. Hydrogens, we had 12, and that was 1 gram per mole. Our phosphoruses, we had 1, and that's 31 grams per mole. And we had 4 oxygens, each at 16 grams per mole. Now what do these equal? Well, 3 times 14 is 42. And make it easier on myself, I'll put grams per mole over top, so everything below that obviously will carry the same units. 12 times 1 grams per mole is 12. 1 times 31 is 31. And 4 times 16 is 64. Add this together and we get 150 grams per mole. Let's inspect the choices. And right here we see 149 grams per mole. And given that many of these were actually decimals to begin with that we rounded, the obvious answer would be this, choice C. All right, number 4. The gram formula mass of a compound is 48 grams. The mass of 1 mole of this compound is what? Well, when we talk about gram formula mass, we're talking about grams per mole. And what that really means is how many grams do we have for every 1 mole of the substance. So if in fact we have 48 grams per mole, well, it would be 48 grams. Just as simple as that. All right, number 5. A compound has a molar mass of 90 grams per mole and an empirical formula of CH2O. What is the molecular formula of this compound? Well, to begin with, we must notice that the molar mass is the mass that the entire molecule has when it is a molecule. And we have an empirical formula. So we start by trying to find out what the gram formula mass for this empirical formula is. So here we have 1 mole of carbon, and we learned from a previous slide that we need to look at this periodic table to find out the mass of each. And carbon has 12 grams per mole. So grams per mole up top there. And hydrogen, there are 2 hydrogens, 2 moles of hydrogen, each with 1 gram per mole, and oxygen, 1 mole of oxygen, each at 16 grams per mole. Now that amounts to 12, 2, and 16. Add these together and we get 30 grams per mole for this empirical formula. But the mass is 90. So how many times does 30, I should do it this way, 30 go into 90? And that is 3. So in other words, we have to take this empirical formula here and triple it. And here's where we find our answer. The answer is C. Number 6. What is the percent composition by mass of sulfur in the compound MgSO4? That's magnesium sulfate, where the gram formula mass, meaning the entire mass of this entire molecule, is 120 grams per mole. So the first thing I'm going to do, seeing that I need to use a formula, is I'm going to inspect my reference table to confirm that I have the formula correct. Here's my percent composition formula, where it says the mass of the part divided by the mass of the whole times 100. All right. So we are looking for this part, the sulfur. And in order to find the mass of sulfur, I go to my reference table, my periodic table to be more specific, and I see that its mass is 32.065. Now I am going to round that to 32. That would be the most common isotope of sulfur. So 32 grams per mole. divided by 120 grams per mole times 100. Now the units cancel out, they're divided by each other, and let me do the 32 divided by 120 times 100, and there's the answer. Now inspect the choices. Well, the choices aren't that plentiful. No, 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 and that's the one that it must be, because what was it, 26.6667, that rounds to 27. The answer is B. All right, now on to 7. Given the balanced equation representing a reaction, we have 4 moles of ammonia combining with 5 moles of oxygen, producing 4 moles of nitrogen oxide and 6 moles of water. What is the minimum number of moles of oxygen, O2, that are needed to completely react with 16 moles of ammonia? So we have to begin with a 4 to 5 to 4 to 6 ratio, and it's saying that the ammonia is being bumped up to 16. So if that's going to be bumped up to 16, how did we get there? We would have had to multiply by a factor of 4. Now if that's the case, we have to do the same with each of these. Multiply this by a factor of 4, and we get 20 here. Now it's asking about the oxygen, and that's the position of the oxygen to begin with. So let's scan our choices, and the answer is B. And last, number 8. A hydrate is a compound that includes water molecules within its crystal structure. During an experiment to determine the percent by mass of water in a hydrated crystal, a student found that the mass of the hydrated crystal to be 4.10 grams. After heating to constant mass, the mass was 3.70 grams. What is the percent by mass of water in this crystal? Well, let me show you what they kind of mean here. Here it is a portion of a crystal I'm drawing. It has a specific geometric shape. That's what crystals have. And within this crystal, we have trapped some water. And at first, when you take the mass of the entire substance with the water trapped in it, the mass is 4.10 grams. But now they said that the student heated it until all the water was drawn off. So let me go ahead and redraw that. Now the water is over here. It would actually be more like a vapor that escaped, but let's just put it here so that we could have our discussion. Now the mass that remains is 3.70 grams. But remember, it was 4.10 grams. So what must be the mass of the water itself? Well, let's subtract out the mass of the substance, the compound with the water, from just the compound itself. That gives us a 0.40 grams. That must be the mass of the water. So we'll put it right here, 0.40 grams just of the water. I'll just turn on my calculator. We're going to need that in just a moment. There we go. Now, if we want to figure out the percent composition by mass, if you remember, the formula was the mass of the part divided by the mass of the whole divided by 100. So we would end up with 0.40 grams divided by 4.10 grams, because remember that was the entire amount, times 100. I already did it on the calculator. There's your answer. Inspect the choices, and it is choice C. Hope this helped.